Good morning, everyone. Thank you for joining us in this parallel session. My name is Sasvan Armanwela from Quasi Laboratory Research Center for Physics, National Research and Innovation Agency, or BRIN. So today, I would like to talk about buccal hexagonal lattice monolayer bismuthane, and particularly the effect of topology to the thermoelectric performance of the bismuthane. We start with the fact that we have many ambient energy sources around us, such as electronic radiation, chemical energy, motion, light, temperature gradient, and so on. In this work, we will focus on how to take an advantage of temperature gradient. The temperature gradient can be converted into electrical energy through a physical phenomenon called thermoelectric effect. Thermoelectric effect, the conversion of heat to electricity, was discovered long time ago by Thomas Johann Seebeck. As we see in the figure, it is the original apparatus used by him, and A and B represent the two junctions, a block of bismuth and a U-shaped strip of copper. When B side is heated, the compass needle is moved, proving that the temperature gradient in a conductor produces a voltage. The voltage is proportional to the temperature difference, and the proportionally constant is known as the Seebeck coefficient. The TA efficiency could be estimated by this formula, which is mainly depend on the dimensionless figure of merit, or ZT. ZT itself depends on Seebeck's coefficient, electrical conductivity, and thermal conductivity. In order to find a good TE device, we need large S, high sigma, and low kappa. Until now, many studies have done to investigate the TA efficiency of various material. However, most of them have ZT less than 1, still smaller than other device, for example, photovoltaic device. Therefore, it is important to find a good way to enhance the efficiency. To do so, we firstly have to know which material is better for TE, metal, semiconductor, or insulator. According to Whiteman-Franz law, it is difficult to have a good TE from metal or insulator. Why? Because the thermal conductivity is proportional to the electrical conductivity. It seems that semiconductor is better for TE material. And if we see this figure as a function of carrier concentration, that's true that semiconductor tends to be better TE materials than metal or insulator. In addition, Higgs and Dresselhaus suggests that by lowering the dimension of material, we will obtain the high TA performance due to the confinement length effect. However, there is a paradox in low dimensional materials when we see the behavior of the power factor by lowering the dimension of bismuth and silicon. So bismuth has significant power factor, but silicon is not. Why? Theoretical study try to explain this paradox. Power factor of any 2D or 1D material can be enhanced by lowering the confinement length less than the thermal Bernoulli wavelength. Actually, many efforts has been tried to enhance the TA performance. In this work, we want to investigate the dependency of topological phase on TE properties. Here, we use bismuthane as a case study. Why bismuthane? Because bismuth-based material is one of the state-of-the-art TE material. Bismuth is also a heavy atom, so it expected to suppress thermal conductivity. Bismuthene has also two-dimension honeycomb structure, so it has low dimension. And last reason is bismuthene is predicted to be a topological insulator. To develop a coherent picture of the relation between topology and TE performance, we perform electronic structure calculations by means of tight binding method. In order to find the tight binding parameter, we first calculate the DFT calculation for band structure and fitting the band structure of tight binding to the DFT and find this parameter. And for the Hamiltonian, we construct the Hamiltonian consists of the on-site energy Hamiltonian, and hopping Hamiltonian consists of first and second nearest neighbor, on-site spin orbit coupling, and the last is stagger potential Hamiltonian. And for calculating the thermoelectric properties, we use a linear Boltzmann transport formalism along with constant relaxation time approximation. And this is the band structure of bismuthene. So left side is the band structure where we do not include a spin orbit coupling, and the right side when SOC is included. So we can see that SOC is changed significantly the band structure. There is a band inversion splitting in gamma point, making the band gap now becomes indirect here. And this band inversion give us an indication of the existence of topological invariant states in the system. And by calculating the band structure of bismuth nanoribbon, we can see that it is true that we found the edge state in the result of the calculation with SOC here. So we then confirm the existence of topological states by calculating the phase diagram of Z2 invariant as a function of staggered potential and on-site SOC. We can see that SOC tends to induce the topological state, while the staggered potential does opposite. Next, we sample 4 cases in the phase diagram to see their TE properties. So we start from the electrical conductivity. Actually, we provide the contribution from bulk state, age state, and the total of them. The bulk state, as we see here, only contribute to the electrical conductivity if the chemical potential lies outside the band gap. In the figure, we can see in the gray area. For age contribution, we can see that for the trivial case, the non-zero sigma inside the band gap is only appear below the Fermi level here, while the topological case, the age states fully contribute inside the band gap here. The age contribution is related with the age state in each case. Yeah, this one come from this state, and this come from this state. For thermal conductivity, the trends largely follow the behavior of the electrical conductivity, indicating the good agreement with the Whiteman-Franz law. However, we can see there is a additional for the thermal conductivity. This comes from the bipolar effect. If you can see from the Seebeck coefficient, bulk contribution for Seebeck coefficient and age contribution has opposite sign, making the thermal conductivity become larger here. You can also see that the age contribution in the Seebeck coefficient largely linear function of mu. So this behavior can be understood from the mode formula. Now we can see the power factor and figure of merit of trivial and topological phases of bismuthane. Actually, both of them show the ZT enhancement, but more significant enhancement could be found in the TO case. The maximum ZT of TR is appear inside the gap, while in the case of TO, it's appear in outside the gap. Yeah, why it can happen is because for topological case, the Seebeck coefficient inside the gap is very small. Although the sigma and kappa is large, but both of them is cancelled out. So as summary, we have calculated the electronic, thermoelectric, and topological properties of bismuthane using tight binding method, and we demonstrate that we can tune the trivial and topological phases by controlling the SOC and stagger potential. And finally, we found that although inside the band gap, the TO phase didn't show the good ZT, but at large doping, we can have large ZT. That's all from me. Thank you for your kind attention.